Hi, today I'm going to talk about a type of chi-square test called a contingency table. Sometimes this is also referred to as homogeneity of proportions, chi-square test of homogeneity of proportions. In a different video, I went over a chi-square test called a goodness of fit test. And this test is very similar. It uses the same chi-squared equation, which is your observed values minus your expected value squared divided by your expected value for each value that you have in your observation table. But the way that the expected values are determined are actually calculated differently than in a goodness of fit test. So I'm going to go over an example that might be something that somebody might study in the Pacific Northwest. Say you're out in the forest and you notice there are flocks of black-capped and chestnut-backed chickadees. Those are two fairly closely related chickadee species, and you're curious how they can move around and forage together, but avoid competing with one another for food resources. And after some observation, you determine that you think that chestnut-backed chickadees forage more in conifers and black-capped chickadees forage more in deciduous. This is a mock data set that I'm presenting here, not any results from a real study. But you go out, you make some observations in the forest, and this is what you end up with. You go into, you actually go into mixed forest. I think that would be preferable in this study, but you're noting what birds are foraging. So each observation is a bird actually grabbing a piece of food from the foliage, and it can be a seed, it could be a variety of food items, but you're looking at what type of tree they're in when they feed. And here you have black-capped chickadee and chestnut-backed chickadee. Okay, and this is what you observe. That you observe that there are black-capped chickadees foraging in conifer trees, 25 of your observations, and then in 40 of your observations, they were in deciduous. With the chestnut-back, you observed 30 observations of feeding in the conifer and 35 in the deciduous. So you want to know if that represents any real differences in their foraging patterns. And to do this, you need to figure out what you would expect to see if they were foraging roughly the same. And I can't just say 25%, 25%, 25%, 25%, because we don't know that it might be that both species prefer deciduous trees. And so we need to be looking at what would be a reasonable proportions of foraging. And so we do that by first calculating row and column totals. And so here, this row total is 55. This row total is 75. This column total is 65. And this column total is also 65. And then in addition, you're going to get the overall total, which is 130. And so you then build a table of expected values. And I'm going to make this table a bit longer so that we can fill these calculations in. And then I'm going to have to make some more space. Okay. So to calculate to get your expected values, you take your row total and your column total and divide it by the overall total. You multiply those two and divide. So for the case with this cell here, okay, so this is black-capped chickadees foraging in conifers. The expected value would be 55 times 65 divided by 130. For chestnut-backed and conifers, it would be 55 times 65, because this column total was 65, divided by 130. For black-caps and deciduous, it would be 75 times 65, divided by 130. And then for chestnut-backs and deciduous, it would be 75 times 65, divided by 130. And if you want to take a minute, you can pause this video and calculate these up with a calculator. So once I do calculate those values, this is what I get. 27.5, 27.5, 37.5, 37.5. You're not always going to get this sort of even expected values, but in this case, it is. So these are your expected values now. Okay. And now you have observed and expected values that you can plug into an equation. And so I'm going to build the equation. I'm going to make this table just a little bit smaller up here. So it's 25, 30, 40, 35. Okay, so those are our observed values, and these are the expected values. And so I actually like to set it up the same way as all the rest of the tables, just to keep things organized. Okay. I'm actually going to make this also kind of long, bigger table, so that we can sort of make space for the calculations. Okay, and this is where we plug in the chi-squared equation. And so we take our observed value, and this field is 25 minus expected, and then you square that value, and then you divide again by your expected value. You do that for each cell in your table. And this one's 40 minus 37.5 squared divided by 37.5. And then this one's 35 minus 37.5 divided by 37.5. Let's square this. So again, I'll give you a moment to go ahead and make those, get those final values. So you can pause it if you want. And so when you make these final calculations, what you get is, from this cell, I'm going to sort of draw a line up here, you get 0.227. From this cell, you get you should get the same value. From this cell, you get 0.167, and from this cell you get the same thing, 0.167. And then it's just a matter of adding all of those values up. And as you can see, just by eyeballing it, you're going to get something less than a value of 1. And in fact, the grand total is 0.788. Okay? So that's what you end up getting for your chi-squared value. That's your test statistic. Now what you need to do is compare that value to your significance table. And we're always looking for a significance value of p equals 0.05 or smaller. Now, I know by looking at this chi-squared value that I'm not going to be finding a significant result. And that's because most of these test statistics, you would need a value of at least 1, usually a number greater than 1, to actually expect to see a significant result. Before I look at the table, though, I need to know what my degrees of freedom are. And you get degrees of freedom in this type of chi-squared test by adding together the rows, number of rows, multiplying together, rows minus 1 times the number of columns minus 1. So we have 2 rows minus 1, so that's 1, times 2 columns minus 1. So our degrees of freedom in this test is 1. And so now I'm going to share a screen of a significance table. Let's see here. Okay. And what you can see is at a degree of freedom of 1, to get a p-value of 0.05, I would have needed a chi-squared value of at least 3.8. My number is actually much smaller than that. It's actually smaller than the significance level of 2.7. So from the data I collected, I can't say with any confidence that there was a preference, a difference in the foraging preferences of these two species. And that's okay. Maybe I need to go out and collect more observations, or maybe at the site or the sites I was looking at, there just weren't differences to detect. But you can use this table to make sure that to check your significance level. So that's chi-squared test for homogeneity of proportions, or also known as a contingency table.